So the second half of this chapter is about logarithms. So exercise 1004 introduces logarithms. The inverse of an exponential function is a logarithmic function. So for example, in year 7 you learned how to solve an equation like this, x plus 3 equals 7. And you learned that the inverse of adding 3 was to subtract 3. So we minus 3 from each side. And logarithms work exactly the same way as that with exponential functions. So here a is the base, x is your power, y is like your answer. What we need to do, because it's base a, is take the log base a of each side. So if I go log base a on that side, log base a on that side. So as I said, log is the inverse of a. So this log base a and this a actually cancel each other out. And this whole side just becomes x. So we've got x now on that side and log base a of y on that side. So if I have, for example, 2 to the power of 3 equals 8, I've there got the base, the power, and the answer. You might call that BPA form. If I now, because 2 is the base, if I take log base 2 of each side, the left-hand side is log base 2, 2 to the 3. The right-hand side becomes log base 2 of 8. As I said, log base 2 and 2 to the power, they're the opposite of each other. They cancel each other out. They are inverse operations. So this side is now just 3, and this side is log base 2 of 8. Now I'm just going to turn that round to write the log on the other side. So log base 2 of 8 is equal to 3. And some people like to think of this as 2 as your base. 8, remember, was your answer, and 3 was your power. So some people like to call that BAP form. Now, essentially, if you see log base 2 of 8, you really need to say to yourself, 2 to the power of what number equals 8? And in this case, it's 3. 2 to the power of 3 equals 8. So you're kind of saying what little number goes in here on that 2 to make a little equation there that is correct. Now, I will just draw your attention to what I've written here. We've already seen in the previous exercise that a has to be a positive number. Even having 0 doesn't really make sense. 0 to the power of anything, well, that's fine as long as x isn't 0, but yeah, if a is greater than 0 is when we do these things. A also in this case can't be 1. If you have log base 1, you're kind of saying 1 to the power of what? 1 to the power of what number equals something? So if you had log base 1, 3, you're saying 1 to the power of what equals 3? Well, that makes no sense whatsoever. So a can't be equal to 1. Also, y is always going to be greater than 0. It's always going to be a positive number, no matter what. And we saw that with our exponential graphs, that we always got a positive answer. Our answers were always above the x-axis. So y is always greater than 0. You can't take the log of a negative number. So in that situation, the domain when you've got log base a of y is that y must be greater than 0. Okay, let's have a look at a few examples. So we've got right log base 3 of 81 equals x in exponential form. So if there are two ways of doing this. We did just talk about how this is 3 to the power of something equals 81. So we could just go straight to 3 to the power of x equals 81. And that's particularly if you have sort of memorized the BAP and the BPA form. Basically the 81 and the x kind of swap order. Another way to do it would be to take 3 to the power of each side. So 3 to the power of log base 3, 81, equals 3 to the power of x. Now 3 to the power and log base 3, those are inverse operations as I've been talking about. So this side is just 81, and this side is 3 to the power of x. Now, in all these questions, they are going to be nice answers. So in order to solve this one, you could think of it as like a factor tree. So 81 is 9 times 9. 9 is 3 times 3, 9 is 3 times 3. So 81 is the same as 3 times 3 times 3 times 3, or 3 to the power of 4. So x is equal to 4. Right, 2 to the power of 7 equals 128. So two ways again. You can kind of swap the 7 and the 128. So log base 2 of 128 equals 7. Or the base is 2, you can take log base 2 of each side. So log base 2 of 2 to the 7 equals log base 2 of 128. Log base 2 and 2 to the power are inverse operations, so this side is just 7. So 7 equals log base 2 of 128. Either method is fine. This method is quite important in terms of understanding for solving exponential and logarithmic equations when they don't have such nice answers. Okay, number 3, solve x to the power, log base x of 16 equals 4. So again, you can go x to the power of 4 equals 16, or x to the power of each side. So x to the power of log base x 16 equals x to the power of 4, and this side is just 16. Now, that is not even an exponential equation, okay? That's a power equation, so we can take the 4th root of each side. So x just equals 2. One thing to think about here is, could it equal minus 2? And of course the answer is no, because as we've already said, it doesn't make sense to have a negative base. So it is just positive 2. Lastly, evaluate log base 3 of 1 on 27. Now, one little trick I like to use for this one is actually to write 1 on 27 in a power form. So this is the same as log base 3 of 27 to the minus 1. And that's the same as log base 3. 27 is the same as 3 cubed to the minus 1. So that just equals log base 3, brackets, so we multiply the powers, 3 to the negative 3. Now log base 3 and 3 to the power, inverse operations, cancel each other out, so the power is our final answer. Okay, these are just 4 special results of log laws kind of thing. So the first one is log base a of a. Well, remember, a means to the power of 1. It's kind of like there's a little power of 1 there. Log base a and a to the power cancel each other out. You're left with the power, so the answer there is 1. Log base a of 1. So you might want to think of this one as saying a to the power of what equals 1. And we know anything to the power of 0 equals 1. So the answer for that one is 0. So anytime you've got a 1 here, you know that the answer is 0. Now you can see that with your calculator as well. We have 2 log buttons on the calculator, this one and this one. And in your calculator, if you press either of those and go log 1, it will tell you that it is 0. That's ln, or the natural log, logarithm natural. Okay, and if I use the other log button, log 1, I also get 0. So log 1 always equals 0. Log base a to the power of x, again, a is the base, a is the base. Log base a is the inverse of a to the power. They cancel each other out. You're just left with x. And finally, a to the power of log base ax, a to the power log base a are inverse operations. That also just equals x. So there are 2 common logarithms that are used quite a lot in various applications. One is common logarithms, which are log base 10. Now, it is a bit controversial whether you can just write that as log x. This textbook does, but really in the HSC it should be much clearer, because there are plenty of times where people write log, meaning log base e as well. So just be a little bit cautious of that one. It really should have the base. The natural logarithm is log base e, and that can also be written as ln. A lot of people think this is an I when they see the button on the calculator. They think it's the in button, but it's the log natural button. Okay, so let's use our calculator to evaluate some of these. So the first one is log base 10 of 27. So press the button that says LOG Okay, on your calculator, the log button, put in the 2.7 to evaluate your answer. I'm sorry, that does come out pretty dark. So 0.43 to 2 decimal places. Now remember I said before that most of these will have pretty, they'll be integer answers, but in this particular case, because it is a button on the calculator, you will get fractional answers as well. Okay, so the second one is log base e of 4. So this time you will be pressing the ln button, log natural button, put in your 4, and the answer is 1.39 to 2 decimal places. Rounding, if the question tells you how to round, do that. Otherwise, a couple of decimal places is fine. Okay, the next one just says ln 5. So remember, again, that's the natural logarithm. So log 5, if you put it in your calculator as log 5, you should get approximately 1.6. And the last one, log base 10 of 0.3. So have a go yourself, log 0.3. Now, one thing here to notice is you do get a negative answer. That's just to 1 decimal place each of those. The reason you get a negative answer is because it's like a negative power. 10 to the power of some negative equals 0.3. So the powers are the bit that can be negative. A real-life application of common logarithms, or log base 10, is about the loudness measured in decibels of something. So the formula for loudness is loudness, L, equals 10 times log base 10 of I over I-O, where I is basically how many times louder it is than threshold level. So I-O is threshold sound. So basically, that's the level at which you can just hear it, but not really. So where sound just kind of disappears for the human ear. And we often compare, this is like a ratio of sounds. Now, I just wanted to point out too that when you come to exercise 10.06, question 7, this formula is correct. The answers in the back of the book are wrong, and I will mention that again when we do exercise 10.06. This is the correct formula to use in that question. Okay, so let's have a look. So firstly, it's good to be aware that sound louder than 85 decibels can cause hearing damage. So let's look at this example. A concert is 10 billion times, louder than threshold level. How many decibels is this? So that's I that we're talking about there. That's the same as I equals 10 billion times I0. Now, I much prefer to write that in index form if I can. We have 10 zeros there, so that's the same as 10 to the power of 10 times I0. So if we put that into the formula, L equals 10 log base 10 of 10 to the power of 10 I0 over I0. Okay, and that's pretty simple to evaluate. The I0s are going to cancel out. Log base 10 is the opposite of 10 to the power, so they cancel out. You've just got 10. So the final answer there, we go 10 times 10, and that is 100 decibels. So that's pretty loud. That's going to cause hearing damage, most definitely. In this final example for this exercise, we say how much louder than threshold sound is a fan that's measured to be 35 decibels. The loudness is 35 decibels. So the formula, remember, is 10 log base 10 of I over I0. And we're basically saying, what is this ratio? So the 35 is the loudness, that's the decibels. So 35 equals 10 log base 10 of I over I0, divide by the 10, so 3.5 equals log base 10 of I over I0. Now remember, the inverse operation of log base 10 is to go 10 to the power. So just like if we had a plus on one side of an equation, it would become a minus on the other. And log base 10 on one side becomes a 10 to the power on the other. And just to show that working out, like when we solve an equation, we normally just write minus 3 under each side. I'm going to just write a little 10 here, 10 to the power of that, 10 to the power of that. So this side is 10 to the power of 3.5. 10 to the power of log base 10 cancels out. So that is just I on I0 on that side. Multiply each side by the I0, so the I0 is coming up next to that. I'm just going to turn it around though. 3.5 times I0. So basically it's 10 to the power of 3.5 times louder than threshold sound. And when I put that in my calculator, I got 3162.27766. So it is approximately 3,160 times louder than threshold sound. So these numbers you end up getting are actually quite significantly big numbers. In both of those examples, we had some really, really, really big numbers there, just for a few changes in decibels. And we're going to look closer at that in a later exercise.